Hi, and very good morning to all estimated lecture. Welcome to our integrated design project video presentation. We are Group 9 and today we will be walking you through our conceptual design of reactor and separator system for a methanol production plant. I am Muhammad Akif bin Muhammad Jad, and through this video you will also hear from my dedicated team members, which is we have Luis Chong Junwei, Adeni Yasmin binti Nur Haidi, Nurfara Batusha binti Junaidi, and Lim Kijun. So let's dive right into the introduction of our process. So before we explain furthermore about our design project, so let me start with introduction first. So methanol is a highly versatile industrial chemical serving as a crucial feedstock for a various product and emerging as a clean alternative energy carrier. As you can see from the block diagram, it explains the flow of methanol synthesis. But for our project, we focus on the conventional syngas-based methanol synthesis route. We aim to achieve an efficient catalytic conversion of syngas into methanol using a packet bed reactor. So followed by a rigorous adsorption-based separation process to achieve a high industrial grade purity of 99.5%.
Now, we are going to talk about our proposed reactor system. This slide presents the selected methanol production route for this project. Methanol is an important industrial chemical widely used in the production of formaldehyde, acetic acid, dimethyl ether, and synthetic fuels. It is also gaining attention as an alternative energy carrier and hydrogen storage medium due to its clean combustion properties. In industry, methanol is primarily produced through catalytic hydrogenation of synthesis gas, or syngas, which consists of carbon monoxide, carbon dioxide, and hydrogen. For this project, the selected production route is the conventional syngas-based methanol synthesis using a catalytic packed bed reactor, which is consistent with the reactor system used in our previous simulation work. This slide explains the technical justification for selecting the syngas-based methanol synthesis route based on engineering and industrial considerations. First, in terms of technological maturity, this method is the most established industrial process for methanol production and has been commercially implemented for over 100 years. It is supported by extensive kinetic and thermodynamic data, which ensures reliable reactor operation and predictable conversion behavior. Second, regarding industrial relevance, this route remains the most dominant technology used in large-scale methanol plants worldwide, particularly due to its compatibility with natural gas feedstock and existing industrial infrastructure. Moving on, the process demonstrates strong reliability and scalability. It is well suited for continuous industrial production, and recycle systems are commonly used to improve overall conversion efficiency. Last but not least, typical operating conditions are within the temperature range of 200 to 300 degrees Celsius and pressure range of 50 to 100 bar. This slide shows the main and side reactions involved in methanol synthesis. The primary reaction is the hydrogenation of carbon monoxide to produce methanol. This reaction is exothermic, meaning it releases heat, and it is favored at higher pressure and moderate temperature. The secondary reaction involves the hydrogenation of carbon dioxide, which also produces methanol but generates water as a byproduct. The presence of water can affect catalyst performance and separation processes. In addition, there is a side reaction known as the reverse water gas shift reaction, or RWGS, which converts carbon dioxide into carbon monoxide and water. This reaction is endothermic and can influence methanol selectivity and overall reactor equilibrium. This slide presents the reaction kinetics for methanol synthesis. The reaction rate depends on several factors, including reactant concentration, temperature, and pressure, as described by the general rate expression. The temperature dependence of the reaction rate constant is represented by the Arrhenius equation, which shows that the reaction rate increases exponentially with temperature. However, methanol synthesis is an equilibrium limited reaction. While higher temperature increases the reaction rate, it also reduces the equilibrium conversion because the reaction is exothermic. Therefore, industrial reactors typically operate at moderate temperatures to achieve a balance between reaction rate, conversion, and catalyst stability.
Hi, my name is Lim Jun, and I would like to present about the reactor type. First, the reactor is selected as PBR, or we can call it as packed bed reactor. The reactor is chosen because methanol synthesis is a gas-solid catalytic reaction, so we need effective contact between the gas reactant and the solid catalyst. In a PBR, the gas flow through a fixed bed or catalyst particles, which ensure the continuous contact and also high conversion efficiency. It is also suitable for high pressure operation, which is very important for methanol production. For simulation, the reactor is modeled as a plug flow reactor or PFR because it assumes no back mixing and allow us to track how conversion change along the reactor length. The operating conditions selected here are 250 degrees Celsius and 75 bar, which are within the typical industrial range. Next is the catalyst selection, which is CuZnOAl2O3. This catalyst is chosen because it is the standard industrial catalyst for methanol synthesis and is known for its high activity, good methanol selectivity, and also the reliable stability. It consists of three components. Copper is the active site where the reaction happens, and zinc oxide acts as a promoter to improve the catalyst performance, and the aluminium serve as the support that provides surface area and structural stability. This catalyst is also suitable for CO2 hydrogenation and work well under our selected operating conditions, which are 250 degrees Celsius and 75 bar. Overall, CuZnOAl2O3 is selected because it is effective, proven in industry, and also well suited for our reactor system. This is sensitivity analysis, where we study how operating conditions will affect our reactor performance. For temperature, as we can see, the higher the temperature, the higher the conversion, because it will increase the reaction rate. However, since the reaction is exothermic, too high temperature will reduce the methanol selectivity. So we choose to use a moderate temperature of 250 degrees Celsius. For pressure, the higher pressure will increase the methanol yield because it shifts the reaction towards the product side. But a very high pressure will increase the equipment cost and also energy consumption. So 75 bar is selected as a balance. For space velocity, lower values of velocity will increase the conversion because the reactant will stay longer in the reactor, but it also will increase the reactor size. So a moderate space velocity is chosen to balance the performance and practically. This slide shows the reactor size calculation using the Levensfeld plot. The Levensfeld plot shows the relationship between conversion and Fn naught over reaction rate, and it is used to determine the reactor volume for a plug-flow reactor. The area under the curve represents the required reactor volume. From the plot, we can see that as conversion increase, the curve will increase sharply. This indicates that achieving a higher conversion requires a much larger reactor volume because the reaction rate decreases as conversion increase. Using this plot, the reactor volume is calculated using Simpson loop, which approximates the area under the curve. So as we can see, our reactor volume after calculation is 246.89 cm cube. This will help us to determine the realistic reactor size for our design.
Hello everyone. Now we are going to continue with our proposed separator system. For the separator system, we implemented an adsorption-based purification process to obtain high purity methanol. After the reaction stage, the crude methanol stream still contained a significantly high amount of water, approximately around 35 weight percent. Since the targeted specification for industrial methanol is 99.5 weight% purity, this water must be removed. Therefore, adsorption is used as the final dehydration step in the purification process. If you look at the process flow diagram on the slide, the separation begins with a flash drum, or also known as separator. The reaction effluent first enter this unit, where a pressure reduction allow the unreacted gases such as hydrogen, carbon monoxide, and carbon dioxide to be separated from the liquid stream. The vapor stream containing these gases will leave from the top of the separator and can be recycled back to the reactor system. Meanwhile, the liquid stream, which mainly contains of methanol and water, exits from the bottom of the separator and flows into the adsorption column. Inside the adsorption column, we use molecular sieve 3A as an adsorbent. This material has a pore size of 3 angstrom. Water molecules are smaller with kinetic diameter of around 2.6 angstrom, so they can enter the pores of the molecular sieve and become absorbed. On the other hand, the methanol molecules are larger, around 3.6 angstrom, which prevent them from entering the pores. Because of this molecular size difference, the molecular sieve selectively absorb only water, which allowing methanol to pass through the column. As the result, high purity methanol leave the adsorption column as the final product with approximately 99.5 weight% purity. Moving on to the operating condition, the adsorption column operates at the temperature of 35 to 45 degrees Celsius and the pressure of 1 to 2 megapascals to remain stable liquid phase operation. During regeneration, the adsorbent is heated to 200 to 250 degrees Celsius to remove the adsorbed water and restore its adsorption capacity. The system also operates in downflow configuration, which helps ensuring uniform contact between liquid stream and the adsorbent bed. Now I will pass the floor to the next presenter to further explain about the adsorption column.
For my part of presentation, I'll be presenting separator design basis and adsorption performance. The crude liquid feed entering our adsorption unit comes from the flash separation described by my teammate Adani. It contains 65% methanol and 35% water by weight. For this conceptual design, we use a basis of 1000 kilograms per hour of crude feed. Our target is to produce industrial grade methanol with 99.5% purity, which means the final product should only contain 0.5% water. Based on a simple material balance, we calculated that we need to remove 346.73 kilograms of water per hour to achieve this specification. So we have selected the molecular sieve 3A as our adsorbent. To model the adsorption behavior, we applied the Langmuir isotherm, which describes monolayer adsorption on a homogeneous surface. This is a well-established model for Zio-like water systems. The Langmuir equation is shown here, which is Q equals to Q max BC divided by 1 plus BC. Based on literature data, we use a maximum capacity Q max of 0.22 kg water per kilogram adsorbent and an affinity constant B of 0.85 cubic meters per kilogram at our operating temperature of 40 degrees Celsius. From this isotherm, at our feed water concentration of approximately 308 kilograms per cubic meter, the equilibrium loading is 0.21 kilograms of water per kilogram of adsorbent. This represents the theoretical maximum if the entire bed reached equilibrium. However, in a real column, not all adsorbent achieve equilibrium due to mass transfer limitations and the formation of mass transfer zone. Therefore, for a practical design, we use a dynamic capacity of 70% of the equilibrium value, which gives us 0.147 kilograms per kilogram. With this dynamic capacity and an 8-hour adsorption cycle, we calculated the required adsorbent mass. The water removed per cycle is 346.73 times 8, divides the dynamic capacity of 0.147, and we also apply a safety factor of 1.2 for operational uncertainties. The final adsorbent mass per column is 22643 kilograms. For the column design and operation, we selected a fixed bed absorption column for this application. This is the most common configuration in the industry due to its simplicity, reliability, and ease of operation. The flow direction is downflow, meaning the crude methanol enters from the top and flows downward through the pipe bag. This prevents fluidization of the adsorbent particles and ensures uniform liquid-solid contact. The system operates in the liquid phase at 40 degrees Celsius and approximately 1.5 megapascal, which maintains the methanol water mixture in liquid state and facilitates efficient adsorption. To size the column, we first need the bed volume. Using the bulk density of molecular sieve 3A, which is 700 kilograms per cubic meter, we divide the adsorbent mass of 22643 kilograms by 700, giving us a bed volume of 32.35 cubic meters. For the column dimensions, we use a height to diameter ratio of 3 to 1. This ratio is typical for fixed bed adsorbers as it ensures uniform flow distribution and minimize wall effects. Solving the equation, we get a diameter of 2.4 meters and height of 7.2 meters. So let's take a look at the empty bed contact time, or EBCT. This is a critical parameter that tell us how long the liquid remains in contact with the adsorbent. We calculated the volumetric flow rate of the crude feed using the mixture density of 880 kilograms per cubic meter, giving us 1.136 cubic meters per hour. Dividing the bed volume of 32.35 cubic meters by this flow rate give us a EBCT of 28.5 hours. What does this mean? It means that our adsorption cycle time is 8 hours, which means we operate the column for 8 hours before regenerating it. Since the EBCT is 28.5 hours, which is more than 3.5 times longer than the cycle time, we have a large safety margin. The column will operate well before breakthrough occurs, which ensures no water slip into the product. Next is the superficial velocity, which is another important parameter. We calculated this as 0.251 meters per hour, which falls within the typical range of 0.2 to 2 meters per hour for liquid phase adsorption systems. This ensures a low pressure drop across the bag and efficient mass transfer.
Next, I will explain the temperature swing absorption or TSA process. As illustrated in this diagram, this visual demonstrates the flow of gases within our purification system. Once the molecular sieve 3A become fully saturated with trapped water molecules, high thermal energy is required to remove them. As you can see in the regeneration section of the diagram, a hot purge gas at 200 to 250 degrees Celsius is introduced into the column. This intense heat effectively breaks the chemical bonds between water molecules and the absorbent surface. The released water vapor is then continuously carried out of the system by the purge gas. This heating process is highly effective in fully restoring the column absorption capacity, ensuring it is ready for next operating cycle. So moving on the regeneration cycle. So this diagram illustrates our dual column continuous absorption system. To maintain a continuous flow in our plant, we operate two columns in parallel, as shown here. While column A is actively in absorption mode, purifying the crude methanol, column B is simultaneously undergoing the regeneration cycle. Once column A is saturated, they simply switch the role. This alternating configuration ensures the uninterrupted production of high-purity methanol without shutting down the plant. So to conclude our presentation, the integration of our optimized packet bed reactor and the temperature swing absorption separator effectively remove all unwanted contaminant. This system successfully meet the industrial target of 99.5% methanol purity. So that's all for our presentation. Thank you for your attention.
For our conclusion, we summarize the key aspects of our design into three main parts. First, the reactor design. We use a pipe bed reactor modeled as a plug flow reactor. We selected a copper-based catalyst, CuZNO Al2O3, which is commonly used for methanol synthesis due to its high activity and selectivity. The reactor operates at 250 degrees Celsius and 75 bar, which are optimal industrial conditions. Overall, This setup ensures efficient gas-solid contact and is optimized for both high conversion and stable operation. Next, for separation system, we apply a combination of flash separation and adsorption. The flash unit helps to initially separate components, while adsorption using molecular sieve 3A is used specifically for water removal. We also implemented temperature swing adsorption or TSE for regeneration of the adsorbent. This combination allows us to achieve high selectivity while maintaining continuous operation. Finally, looking at our overall outcome, our process is able to achieve a high methanol purity of 99.5%. We also see improved conversion and stable operation throughout the system. Most importantly, the design is practical and suitable for industrial applications. In conclusion, our integrated reactor and separation design provides an efficient, stable, and industrially feasible solution for methanol production.